Alrighty then. The thing says we're alive, so we must be alive. Hey guys, what's going on? I'm realizing I don't have the additional light here. I apologize. What a what a terrible host. Here, yes, yes, professional YouTuber. Turn on the kitchen light, why don't you? All right. So today they're in Planck Week. I know it sounds like Shark Week with a whole bunch more numbers and don't worry. It's just stuff doing things. Now, it might be doing interesting things. Perhaps there are things that are beyond our comprehension at this time. It would be real great if we could intuit what is going on, I claim. All right. So, as folks are rolling in from all over the internets, the YouTubes, the Twitters, the skies that are blue, yada, yada, yada. I forgot to post the Discord. These things happen. We're going to be talking about the Planck length today. So, what is the Planck length? Oh, let's actually utilize the tools that we have, maybe. I don't know. Would that be smart? Again, race. I haven't taken this poster down, but let's just do this. Because you got a board, you might as well use it, right? All right. So the Planck length first. Let's do our little, bring up our little illustration here because, well, it's going to show us what the heck we're talking about. Okay. So within physics as we know it, basically we have certain, some may say, natural units. Basically, when you combine different constants of nature, you get out units that end up having a value within the system as one. I would say that they are the basis, the building blocks, the ones of the system, and then we parameterize them by different units, which end up giving us ones of reference. So, like certain calculations, I'll say it's like, all right, we're dividing like the Planck mass by like the one of mass by the one of reference, or something like that. Now, again, does that even make sense? I don't know. That was one of the things I was trying to figure out the whole from summer school, and it's like, do I have an absolute clear answer that I can point to and say this is what makes sense? As of right now, I only have like the transformations between the things. As soon as you have a coherent system of units, basically the coherent system of units is, well, let's just do this. Second page, coherent units. Now again, we're going to go to our friends at Wikipedia. We can take this as it is. Okay, again, take with a grain of salt. First level approximation. Oh, there we go. All right. So, yeah, there, bada boom, bada bang, coherence. Okay. So, at least according to Wikipedia, again, first level approximation, a coherent system of units is a system of units of measurement used to express physical quantities that are defined in such a way that the equations relating numerical values expressed in the units of the system have exactly the same form, including numerical factors, as the corresponding equations directly relating the quantities. It is a system in which every quantity has a unique unit, one that does not use conversion factor. The conversion factors of units is the conversion of the unit measurement in which the quantity is expressed typically through a multiplicative conversion factor that changes the unit without changes the quantity. Okay, so quantity with corresponding. Oh, I don't know. Does that ruin the dimensions of coherence? Because that's what we're doing. Hey, maybe it doesn't make sense at all. Change the unit without changing the quantity. Well, that's. I'm gonna click on this for more. I think this might just answer my question. See? It was totally good we did this. I'm basically just barking up the wrong tree. Conversion of units. Conversion of units is the conversion of the unit of measurement in which a quantity is expressed, typically through a multiplicative conversion factor that changes the Oh, okay. Multiplicative conversion factor that changes the unit without changing the quantity. Okay, this is often loosely taken to include replacement of a quantity where the corresponding quantity that describes to include replacement of a quantity with a corresponding quantity that describes the same physical property. Is this like kilograms and pounds? Unit conversion is often easier within a metric system, such as an I, due to the system's coherence. Precision and accurate significant figures. Engineering tolerances. Oh, foot versus the survey foot. Okay, 1 foot. That's 12 inches. Okay. Using old measurements. For some purposes, conversions from one system to another are needed to be exact without increasing or decreasing. That the conversion may not produce the exact same expression. Okay, because we're doing miles, hours, miles out. Oh. Okay, the rules of algebra, factor label method can be converted to meters per second using a sequence of conversion factors. Okay, each conversion factor chooses a base relationship. Oh, so you're only going to have so much. Okay. Which is then simplified because the A is enemy variable physical quantity, but a dimensionless one does not change that quantity. Once this and a conversion factor per second, units cancel out unit miles an hour, 10 miles per hour converts. Okay. Okay, so it's easy to do it as long as the system is coherent. So I think that's what we're saying. Okay, I still didn't necessarily find the answer. Okay, my apologies. Let's get right back to it. All right. So what are we talking about? We're talking about the minimum unit of length. We're talking about the minimum notion of time within a coherent system before. Let's can we get okay, we'll just do this. No, I like it to be bigger. There we go. Do this. All right. Okay. All right, list of coherent units. So this is for SI. So you got frequency, the reciprocal of time, force, mass times acceleration, pressure, Pascal, force, which is expressed in newtons, divided by area. Oh. Energy, force, the newton times distance, so times length. Okay. Hour is energy divided by time. Potential difference. Oh, that's actually what the technical definition. The volt, power expressed in watts divided by electric current, amperes, electric charge, the Coulomb. Electric current times time. It's equivalent radiation dose receiver energy divided by mass. Ooh, okay. So any okay, energy. Okay, so I remember I think it was Kyle Hill or something. He had like a Patreon post or something where it's like, or a video where he uh he had these things. He's like, I totally thought they were all the same thing. I think they're just different magnitudes or taken with a different context because it's you're like, all right, energy. It's like uh energy divided by mass, energy divided by mass. You're like, wait a second. What's the difference? It's the same dimensionality. Now, magnitude, what is the difference? I forget this. I looked it up. Uh, Wolfram Alpha. So it's the gray. The gray was event initially like the definition of a kilogram was like 1 cubic deciliter of water at whatever time. Oh, unit. Sorry. Gray. Okay. So it's the derived SI. So energy is mass times speed squared, which is length squared divided by time squared. Because we got a negative two there. All right. So it's literally only got those units there. So, and then we had, what was it? Sievert. S-P. Sorry. Right. So again, same units there. What the heck is it supposed to be? It is 1 joule per kilogram is okay. It's literally the joule. It literally is the. Huh, that's interesting. I think it's used for different. Never mind. I have no idea. I had an answer that made sense at the time. I don't know. I think it was totally forgot. Apologies. Brain farts. All right. Let's let's say it was a magnitude or like the foot and like the meter feel like, but no, but they were saying the same thing. I don't know, different industries. Hold on, go back. Oh, that was Planck units. Where are we? Coherent. Let's look. C for is the international stochastic risk of ionizing radiation. Okay, so basically that's for people. Ionizing dose, the absorption of 1 joule of radiation per kilogram of matter. Okay, so one is basically defined for people, and one is for just other stuff. Uh, is important predicting likely acute health effects such as acute radiation syndrome, and used to calculate the equivalent dose using the sievert, which is measured of the stochastic health effect on the human body. Okay, all right. People, stuff, people. People are made of stuff. Sounds like one is more medicine and one is more chemistry, I believe. Cool. Okay. Radioactive activity, the background girl. So basically, it's just the inverse of time. So basically, that sounds kind of like frequency. Capacitance, farad. So that's charge divided by potential difference, or volts. Electric resistance, ohms. Potential difference divided by electric current, amperes. You can also multiply electric current by c, or the speed of light. Um, I don't know if that's just where you get the, like, it's the Planck impedance. I think it's impedance. What is it? Ampere constant. Let's see. Ohms. Electric resistance. Okay, maybe that's something else. What was that? That was volts divided by current. Volts divided by current. Like voltage divided by Planck current. Oh, this is just Ohm's law, I think. All right, yeah. Because current equals resistance times or divided by voltage, or voltage divided by resistance, I believe. Wait, that's what they said. Dirk. Voltage, yeah, okay. Yeah. I'm so dumb. Let's see, this is what happens if you never completed an actual full physics class. Electrical conductance, the ampere divided by volts. All right. Volt. Okay. And volt divided by current. Yep. So that's yeah, Planck electric impedance. There we go. All right. Blah blah blah. Electrical resistance, electrical inductance, magnetic flux, Weber's potential difference, volt times time, seconds, magnetic flux density, Tesla, magnetic flux to Weber divided by area, square meter. Oh wait, I have these just on the chart right behind me. I know, super derp. My head is it's yeah, it's that little circle behind us. So basically, that's a whole bunch of stuff. What the heck does it mean? Okay, see, when you actually image, you actually have a picture that you could demonstrate. So let me do this. Stop. Dun, dun, dun. Sorry. Arthritis got memed into me. So basically, what we were just talking about is this thingy here. Okay. What the heck is this? Okay. Don't don't mind the arbitrary mean of a maximally tangled Stephen Wolfram over here. And zeta equal of elementary time, excuse me, elementary energy divided by elementary time, which if when you just do the math, it comes out to be the Planck power. So it's a minimum of energy divided by a minimum of time. You got two ridiculously small things. It's going to equal a ridiculously big thing. What's the Planck power? The Planck power is like 10 to the 5 solar masses per second, i.e., it puts out the mass energy equivalent of Sagittarius A star, whatever that super dense thing in the middle of our galaxy we believe that's there, whatever that mass energy equivalent of Sagittarius A star, a maximally entangled observer, whatever that might be, would basically output that mass energy in 21 seconds. So yes, in 21 seconds, a maximally entangled observer would output the mass energy of Sagittarius A star. That's freaking crazy. Oh, but yeah, the whole SI thing is, yeah, you got your seven base units here. So you get meters, kilograms, Kelvin, candela, moles, amperes, and seconds here. And you can see over here, all right, you combine your meters and seconds, you get speed, meters, divide by seconds. Oh, look, get meters, divide by seconds squared. Ooh, okay, at that point, now you've got acceleration. All right. Now acceleration, mass times acceleration. Oh, guess what? We get the Newton. We get a unit of force there. All right. Oh, and guess what? If we add in another meter there, oh, it goes from acceleration to energy, the joule. I really should have a table for this rather than just hope it. Never put it in. I need to add that to my community post because I'm a terrible, lazy individual. All right. That's a lot of bloviating. Let's quit that preview. All right. Go back to our go back to our friends over here. All right, so the Planck time, we go over here. Oh, the whole reason I went here in the first, did they move that diagram? Oh, they moved it. Is it not here anymore? Oh, never mind. Apologize. Oh, obviously just looking for reasons to blame other people. All right. Dimension related coherence. Notes, putting this out there. This article section possibly contains original synthesis. Source material shall verify, mention, relate the main topic. Relevant discussion may be found at the talk page. Okay. So here's this whole thing. And again, this is from Wikipedia. I first learned about this in a video from Thad. You can take that however you would like. Each variant of the metric system has a degree of coherence. The various derived units being directly related to the base units without the need of intermediate conversion factors. Additional criterion is that, for example, in a coherent system, the units of force, energy, and power be chosen so that the equations force equals mass times acceleration, energy equals force times distance, power equals energy divided by time, hold without the introduction of constant factors once a set of coherent units have been defined in physics. Those that units that would automatic those units other relationships in physics that use those units will automatically be true. Einstein's mass energy equation E equals mc squared does not require extraneous constants when expressed in coherent units. All right. You got the different system, the CGS system, SI, the broadly used one here. So, okay. Thank you for our coherence. We continue. All right. So we went over the Planck time. Why? Because well, that seems to, at least within these general units, and including the Planck charge, which gives us the constants that we need. H bar, big G, and then we get Boltzmann's constant, and then you need some form of the electric constant. Uh, and then basically you can reproduce the stuff and things that we measure dimensionally. Yeah, you might see angle and stuff in there every once in a while, but to be fair, that diagram I just showed you, they literally just have it appear. It doesn't even like go from like meter because it's a length. It's in regards to two lengths. So I thought you should at least have like a length and then like a dotted line was division. I forgot to mention that solid lines were multiplicative relationships. Dash lines were division relationships. I feel like you should at least have like 1 meter and then divide by 1 meter to get like at least a reference angle. Just throw it in the middle of the chart, and that I basically just copied that general chart that was on I think in this website, and then I just put it in the different format. That's all it was. I just went into what is it? I don't know, Keynote. I think that was the program. mashed it up. I tried doing some code, and I was asking it to do a lot, and I didn't have enough experience coding or time, so maybe I could have done. I was just lazy, then I'll say. All right, so we went over the Planck time. So as we can see, we have these units here. Four base Planck units here, and then you have some notion of charge. So we did time. So the Planck time, it's small t sub p, capital P there, equals the square root of h bar, big G divided by c raised to the fifth. So the Planck length, again, surprisingly, or perhaps not surprisingly, it's the exact same setup, except instead of dividing by c, the speed of light in a vacuum or in the vacuum medium, whatever that might be. Um, it's basically rather than c raised to the fifth, it's the speed of light raised to the third. All right. So we're losing technically four dimensions of input there. We're losing uh, two Planck lengths and two Planck times because it's a factor of c squared. Let's just length divided by time, and the whole thing's squared. So it means we got two lengths, we got two times. There we go. Okay. I realize I'm probably angering a lot of folks saying it very casually, but this is just how it seems to be algebraically defined. The Planck length is the square root of h bar, the elementary unit of action, times big G, the Newtonian gravitational constant, divided by the speed of light raised to the third power, and we just take the square root of that. So go over here, you do this whole thingy. It's all right. You just go to what was it? H bar, big G, boom, 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 and that's divided by speed of light to the third power. Let's see what we get. Unrooted. Oh, look, we get the Planck area because that's what happens when we don't have the little square root there. So if we want to get into a single dimensional measure, just root, bada boom, bada bing. And again, if you're going to some of like the physics stack exchange board, some folks will. There's an interesting discussion there. Some folks are like, well, square root of the Planck length is just kind of a convenience. Maybe the Planck area is more foundational. It's like, why? Well, you don't need to take the square root of that. Maybe that maybe that's a good thing. Maybe I don't know. Maybe we're just all rooted somewhere somehow. Um, uh, hopefully, I made a mathematician or something joke laugh, but I'm sure it wasn't funny because it probably wasn't accurate. But so this is how you get it. You just throw this stuff in here. Again, you can just use natural language if you're using Wolfram Alpha. Uh, and then you get this here because we know five significant digits. We have seven with error. As you can see, we got comes out to be the value in SI units. All right, it is 1.616255. An error of 18 in the last two digits means that we believe it could go up by 18, it could go down by 18 on these last two times 10 to the minus 35 meters. Okay, how the heck small is that? A yard is like, or was it? Oh God, stupid American yards. A meter is about a pirate pace. You take like one good pace. All right, that's about a meter. All right, that's 35 orders of magnitude less. What the heck does that even mean? Okay, let's see. Billions and nine zeros, trillion. It's like one tenth of a trillion, trillion, trillion meters. Approximate magnitude. Because a trillion, trillion, oh, excuse me. Trillion, it's a trillionth, trillionth, trillionth times 10 of a meter of magnitude. Yeah. So a proton, we believe at least its charge rate is like 10 to the minus 16 meters. This is, yeah, yeah. It's a trillion would bring us 16, 12, 28, 28 plus we need. Okay, it's like 100 million trillion times smaller than a proton. Eensy weensy, not zero. Interesting. Now, within the Wolfram Physics project, there's believed to be some subplanking and stuff. So, I think, according to my calculations, it was around the magnitude of about 10 to the minus 90 or 91 meters, maybe 92 meters. This is the elementary time with about 10 to the minus 100-ish meters. And they have a magnitude difference of 8 because of the speed of light. So, but at least according to science, as we understand it within the generalized standard model of physics, this is the minimum of length. I.e., once we get here, we can't go farther. Basically, stuff and things stop working because now how do you keep on dividing past that? I mean, you divide by zero, that's going to give you a problem. Only there was an infinitesimal or something like that. If there's some notion of discreteness, then we would literally have something almost like infinitesimal calculus, but with some form of a limit. It's ah, welcome, Rick. So a radical power table calls the square H and G. I think we did that. That was very interesting. You have a coherent system of units. Zero is always zero. Oh, oh. Because conjecture calculus has its limits. Well, I mean, just because we say it's an infinitesimal, I mean, that's just the convenience there. I mean, what would that mean? That maybe we could actually figure out what's going on. That would be very awesome. But where are we? Where are we? All right. So we've got the Planck length. Oh God, what am I even going to say about the Planck length? Okay. So all right, let's just relate it to different things because, well, it's something that we at least have a notion of. And heck, the interesting thing is a lot of times, even with, oh, the intricacies of language. One of the things with time, or the things that we have with time, is that time, yes, I was going to use time twice there. Uh, it's even interesting when you hear somebody like Richard Feynman saying he'll use time in two different contexts, and you realize it's like, perhaps we need some better words for what we're discussing there. Uh, the where oh, time is often measured with lengths, or that's one of the things that we do because now it's well. To be fair, we're using the cesium clocks because I think within 1 second we get to like 10 significant digits. Uh, whereas if we had the speed of light, we had it to like 9. So that's why like our units of length. They're kind of cut off by 9. Yeah, we got H bar to 10 significant digits, but things don't quite line up as we may hope them to. Or I don't know. I don't know. Maybe we just don't have enough precision data. We do have a lot of measurements. I know Thad's been spending a lot of time working on those. So, but yes. So the interesting thing is, what's the factor between time and length? It's c squared. So all we need to do is you just make that up to 5. Why is it 5? I don't know. It's heck. Why is it? Why are we dividing by 5 for the limit of time and then for temperature, which I don't know. Maybe we can even express seems to be a convenient thing, but I think Rick had mentioned maybe we could just absorb that into electromagnetism or some of those effects. It's again, however we parameterize it, it is quite interesting. And talked to Casey a little bit. I'm like, what does category theory say about I don't know physical dimensions? Can we measure these things? Or oh no something something the Buckingham pi theorem is. Oh my God, I forget her name. She was one of the presenters at the Wolfram Physics physics program. Uh, oh my God, I'm so sorry. I forget your name. It will come back to me later. But she had recommended for work on the project, the Buckingham pi theorem, because apparently it relates different dimensional units and then could somehow get it to see if like there was some physically or important relationship. I'm not sure if it was dimensional. I think it's something about setting up a matrix, looking at the determinant and stuff. And yeah, I've done some of that stuff. I'm not knowledgeable enough, and I've spent not nearly anywhere enough time working that out. So, all right. Oh, sorry. Back to you. All right. So we add our c squared, and there we get 10 to the minus 44. So I'm just going to take the square root off. Let's live dangerously. Oh, look, we get time squared. Okay. Go back there. Oh, do the 3. All right. We get length. We don't have that on. We get area. And we get the Planck length. We can add different relationships. We got length. So we can divide by the time. All right. You're basically going to get the speed of light, or giving us 6 digits. All right. Speed of light. Boom. And just, I don't know if this was literally like just part of the project. What is this? Hydraulic conductance. Don't know what that is. It sounds something like machinery and stuff. So but here's the thing, and there's also, oh, hold on, a basement. I've looked this up before. I don't even know what it is. It's just the meter second is a basement. Kinematics, a basement or a position is a measure of sustained displacement of an object from its initial position. Oh, It- that's the thing. It's like I have no idea where this goes. It's like imagine, listen, whatever you think of Wikipedia or Wolfram Alpha or stuff like that. If you're not a genius and you don't know what these things are, maybe at least initial introduction might be useful. Perhaps it doesn't have all the rigor that perhaps a professional mathematician may want, but at least for a dude like me, I find it useful. All right, synonym to absposition in portmanteau of the words absence and position. Oh, it's not. It's going to be changing. So we go get our interval of x, and the derivative of time. So over time it moves. Oh, time meter. Okay, so just meters times seconds, not meters per second. Integral displacement. Okay. Factor G. I don't even know what that was. What did it bring me? It's okay. So that's not even a word I'm seeing anywhere there. Okay. So we go back. A penthouse. Uh, it's commenting he discreetly preferred unlimited calculus. I see what you did there. Let's see. Uh, welcome, Morgan. Morgan is conjecturing about everything is the copper coil. Is it the Ouroboros of aluminum? I'm sorry. I'm sorry. That was mean. No, aluminum isn't copper. It doesn't conduct as well. Uh, yeah. A penthouse for 500, yes. Uh, hey, all I know is Tesla apparently did a lot of magical things with coils that apparently his position of, listen, gonna send power all across the world via like the ionosphere or however he set up that Earth-based circuit type thing. And the folks from the large banks were like, yes, Mr. Tesla. Yes, Mr. Tesla. And then he uttered the phrase that totally didn't doom him. And we'll give it away for free. All the bankers walk out, and the Tesla's tower left to rot now. I have no idea if that's a true story. That just seems like an extremely plausible story, just based upon lived experience. So, okay, could be wrong. Take it as it is. All right. So let's go back to our units here because we're literally just breaking these up into different things. Okay, so even just all right, you get a maximum speed. So all right. I'm gonna do this. I'm just gonna keep on writing out the speed of light because that's easier to interpret. Because C means, do you mean the Mandelbrot C? Ah, what are you adjusting in here? I think that's the complex factor you add in there. It's been a while since I Mandelbrotted. Let's see. So if you get the speed of light, all right. Well, okay. So light is, let's tell us. Oh, and again, the only reason I can really do any of this stuff is I just get all the data here for me. It's like a strategy guide for a video game. It's like, all right, what do I need to know about these encounters, these game dynamics and stuff like that? All right, it's you have your thing. Okay. This if physics was a game, so to speak, I'm saying it is. Good. If we were playing the game of sciencing, you got a speed. This is our maximum speed. It's the limit within the game. It's kind of like in I can't say Final Fantasy VII, but for at least some Final Fantasy games, assuming there wasn't one of those magnitude thingies. Typically, your maximum damage is 9,999. Okay. This is essentially your maximum of a thing. Rather than damage, it's a speed. Okay. This is how I grok it and understand in my mind. All right. That's a speed. What are the things that do it? Well, damage is very often is you have a weapon, you have a strength score. Your strength score is going to output your damage modifications, and then you might have different affecting terms or things that go into that as well. But all right, so rather than a weapon in your strength score, it's just the dimension of length divided by the dimension of time. When you're using Planck units or natural units that correspond with our dimensions of measure, or at least their quote unquote natural bases. Uh, you have a unit of length divided by a unit of time. Okay. So we had that there. So it's like, all right, speed of light times the Planck time. So we had the Planck time essentially on bottom. Uh, Oh, look, you have the Planck length because it's length divided by time. You're just multiplying by time, so the denominator just cancels out. Because you could also view this as Planck time, speed of light divided by one, or Planck time divided by one, because it's literally like length divided by Planck time, according to our least magnitude understanding. And then if you're going to multiply it by the Planck time, to be fair, it's technically you could say it's being divided by one. Hold on, let me make this look right here. Okay. This just makes it easier to visualize. So this is something you could say that there's always a one there. There's something that Thad pointed out to me. It's like, yeah, very often we just don't say that there's one. You could even express heck, just do all this. Maybe there's a better way to keep track of stuff. I don't know. One Planck length divided by one Planck time. All right, and then one Planck time divided by one. That's nothing. There's just a one there. But you see, if you're multiplying this, one is one, but that times that, these just cancel out. So you just get one Planck length divided by one. One Planck length. I understand. Yes, it's direct. It's naive. It's also a way that I hope to conceptualize things. And also, one of the things I've learned from Stephen Wolfram is explaining things is actually one of the best ways to try to get a grip on it because, like, I might have an idea in my head. I'm like, oh, of course that makes sense. And then I actually try to verbalize it and explain it to other folks and not be completely spewing hot garbage. Occasionally, it might be a little bit more difficult than it appears, especially if you're trying to talk about something that maybe you weren't fully trained on. I don't know. Does that give one an advantage if there happen to be a particular other way of looking at things? Perhaps that may give us a little bit more explanatory power, per se. Maybe. Uh, Morgan's commenting about where all the copper deposits are located on Earth. I think they're in the ground, around the mantle. I don't know. It's I think there's some iron something supposed to be an iron molten nickel core and then a solid core and depending on the geological looks there might be an inner core now. It's I don't know, it reminds me of World of Warcraft. I'm like, wait a second, we gotta go to the molten core and how many levels down do we need to go? But yeah, and also hearing about all these other like little blobs that might be the planetesimal. Oh God, is that a word? Planetesimal? Planetesimal a thing? Planetesimal. Stole that from somewhere, didn't I? A minute planet or body that did not come together with many others and the gravitational form of oh, because the planet, by the definition, it must be at least a spheroid under its own gravitational effect, so to speak. That's why Pluto is it's a dwarf planet or something. It's still a planet to me. I don't. It's still Pluto is still a planet. Twitter is still Twitter. I mean, I don't really care if you call it X, but it was Twitter. It's the bird app. So a little planet, a minute planet. Uh, uh, believed to has form. Okay, so I didn't just make that word up. Okay, so I did hear it somewhere. Okay, long story short, you have basically the oh god, it's going to be terrible. The quote unquote corpse of whatever we believe was it Thea or something like that. We believe was a massive impact that gave us a really big moon. All right. Speaking of moons, apparently Uranus, a newly discovered moon, has been discovered. Yes, yes, I used the same word twice. Uh, I realized I said that after watching an Anton Petrov video with Fizz, just 'cause- so we could talk about Uranus finding a new moon and its properties, but that was totally fake science. That was like it was discovered 150 years ago, and it was I just hadn't heard about it, and I totally misrepresented something, so I had to rename it. And you realize in the middle, it's like, yeah, this isn't new. It's just new to you memes. It's like, good Wolf Girl. Thank you for pointing out my foible. But now we can do an episode and actually talk about a new moon. It's totally a prediction. We're finding new Jupiter moons and Saturn moons like all the time. Why? It's like, oh, imagine you're millions of miles or kilometers away and you're trying to detect something when there's something very big and much brighter, like right there. And you would also need to be lined up so it's not being obstructed. It's not a very bold claim. Where are we at here? Okay. So this is just kind of how I like to think about it here. Let's go back to our point game. Let's see. Okay, so da, 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 da. So it's different factor by the root 2 pi because of the modern definition. I'm using h bar rather than h. Yeah, because of the 2 pi factor there, just rather than having to write 2 pi everywhere, we just say elementary unit of action, go. It's an interesting thing, and I know Fractal Woman has pointed out that maybe we should make these things more clear or whatever it is, because it's like joule seconds. You're like, okay, that's a crazy thing for a unit of action, but it's like, okay, you could write it like joule seconds. I'm like, all right, joules times seconds. That seems to be. Wait a second, we were talking about mass times uh uh what was it time? Oh, we had a basicity. I think we abasement. Sorry. Abasement is length multiplied by time. Okay. So now we're just kind of multiplying by time. That's like, wait a second. Wait, we're multiplying by time. And then I've seen this before. I think even CodeEdit has it this way. It's you just divide it by hertz. Goes per hertz. Okay. Oh, look. It's gives you the Planck's constant. Named unit system. What? Well, that's not correct. Unless they changed it. Because it's literally joule seconds. Wait a second. Is, yeah, conversion from other units. Yeah, that's 1 joule. Or joule second. Yeah, it's got the rounding error in there, but it's like, again, it's only place that can digit it. Units of actions. Yeah, mass, length, and then time in the denominator. What? Oh, because it's based on energy. Yeah, because joule is energy, and then when you divide by a free. Wait a second. Okay, because when you divide, that would be the same as multiplying by seconds. All right, because it's just the inverse. You're just doing the inverse thing. Uh, why isn't that in definition? You write it out. Hurts. Should have it. If I do this, the Planck energy by Planck frequency, just going to give us h bar. Yeah, reduce Planck's constant. Yeah, understand that. Oh. No, this is an SI. Hertz is in there. Oh, this is an error. It's unit. SI derived. Just do energy divide energy by frequency. That just seems to be a bug. Yeah, because this thing energy divided by frequency. Yeah, because if you divide it by seconds, that would give you power. Because that's energy divided by time. If you just divide by frequency, it's doing the inverse. So you go from 2 units of time in the denominator to 1. You're just missing this? Doesn't just have joule second. Huh. That's interesting. All right. Bugs. Dun, dun, dun. Not a named unit system. That is weird. That is just code at H bar. Then Jules, I think the other ones, I don't know. There's a math. I was like the math and physics channel or whatever. Uh, yeah, he's like, he wrote it down the other day, and it's like joules divide by hertz, and I'm like, oh, duh. That's energy divided by frequency. Wow. Seems to be a different way to look at things. Might it be useful to occasionally look at things from a different perspective? I would think so. Where? Hey, Keisha. It's good to see you. No. We're just going over. We're just going to do Plank Week, which is perhaps not as exciting as Shark Week, less chompy stuff and things. But we were talking about how at least according to hold on, we'll have a little fun here. So let's give ourselves a little play the clip. So, or if we're going to go bound into speculation and at least what might not be within the standard model of generally accepted physics and stuff, let's give ourselves the
Although
warning.
this is going to be weird, and it's going to be about a different.
Title of the conference was something like "Ground Truth" or "Turtles All the Way Down," and so it seems as though there's one Ruliad. I don't think it rules them all, and it might be just hyper-rulial turtles all the way down.
Yes, it's on the back of an infinite number of hyperrulial turtles. various people are commenting on the outrage of hacking the universe on a MacBook Air.
We were just discussing how a maximally entangled observer, technically, according to the Wolfram Physics, the framework, a maximally entangled observer with output or whatever their unit of zeta, basically elementary energy divided by elementary time equals the Planck power. But their units are they are scaled by essentially, at least what I did was the Planck flux, and it seemed to replicate their initial estimates. They were using like the Hubble time or something, and a whole bunch of transcendental equations and logarithms. It replicated within one magnitude, derived in seemingly a very different way. But oh, long story short is that's highly speculative. I have no idea if that would actually be the case even within their framework, assuming that that's a way to get to what's going on. Uh, Again, I don't think there's any one necessary way you could particularly get there. Maybe there is, but I feel like there are different ways to learn different things, and ultimately, however one thinks about it, if you can figure out what's going on, fantastic. Then you just need to help lay it out and be able to convince other people. And again, it's like you could add as many epicycles as you want, be like, well, this, and we're going to modify this. It's like, that's why it's like, well, people like hate on the standard model and stuff like, oh, it's not complete. Oh, I know it's not complete, but it's like, all right. So if you're going to do something novel, you're going to have to, if you're going to change something, are you changing it? And even if you can explain something else, are you breaking other things? Because those other things break, and it ends up being down the line where it's like basically, if whatever theoretical framework you have don't hold water, what good is it? So uh that's the thing. Because I've seen people say, well, you can do these things, and it's like, okay, maybe. Well, what happens down this? What's this? And there's also, at least what I learned in high school science is like, listen, scientific method. All right. You have some observed phenomena. Right? Try to formulate a hypothesis. You test your hypothesis. How do you test it? You try to account for the infinite number of potential things that could be affecting this, understanding that you can't account for all of them. Uh, or at least that's the belief thing. Uh, Basically, since we have imperfect information, we're trying to narrow down the potential factors affecting whatever it is as much as we can. And then we continue to try to do science, and i.e., explain more with less. Ultimately, at least for me, that's kind of the goal, or at least what I've heard. So basically, the general thought process is we are attempting to find computational reducibility within our world. Why? Because when we do find pockets of computational reducibility, we're kind of gaining a superpower, a shortcut to do very useful things. Listen, all I'm saying is I've literally had to use use a screwdriver by hand. Power drill makes it a lot easier. Now, just because you have a power drill, does that mean that you want to use it? If you're trying to do something a little bit more sensitive, like, I don't know, maybe like a delicate lock set, you might want a precision screwdriver and be a little bit more gentle there. Uh, Again, particular tool for the job. Maybe you want to do all these other things again and again and again, but yeah, again, it ultimately comes down to, I think, a matter of usefulness. What can we do about it? Does this help explain our observed phenomena? Uh, you can just come up with an idea for it. Because even like right now, is it the within general the world of physics and the cosmology as we know it? It's like, yeah, we don't know what like 95% of the stuff is out there. Like, all right, so of all the visible like matter and energy and stuff we can see, it seems to account for about 5% of the stuff that we can see within our observable universe. Okay. Now again, I'm sure this. some discrepancy, and it's then depending on how you're measuring things. But okay, according to at least what we have, we don't know what like 95% of the stuff in our realm is. Because the remaining amount of stuff is like it's about like 20% or so, like 25% dark matter, whatever that may, or the quote unquote dark mass effect that seems to be out there, whatever that may or may not be. Uh, and dark energy, whatever the heck that may or may not be, because we have some value of measurement, energy density, but if we interpret it as some form of a cosmological constant, apparently we're taking 8 pi, dividing it by the Planck force, and then we output in inverse meters squared. But no, again, it's the spreading apartness of things. So, okay, that kind of makes sense and everything. If you go through the dimensions, okay, I can kind of see that. But I apologize for my rant. Oh, the whole point about this is maximum entangled observer of the Planck power. I got to show this calculation because this is just fun. All right, so let's go back to our friend here. Sorry, let me make it there. So just real quick, boom. So if we do something like just because those things are divided, and if you use the same scaling factor for whatever those little elementary things for the Wolfram calculation, it ultimately if you're scaling both those terms, basically they're putting in Planck energy and Planck time and then scaling them. But if they're both using the same scaling factor, i.e., here's where we go. Okay. I can actually implement the little diagram here, so it wasn't just for brain fartiness. Uh, okay. So here's the thing. Oh, let's just do the exact thing. Like energy divide by. Okay, put it around both of these guys. Make it clean. Just seems to be how it likes the brackets. All right, and then Planck time. Boom. Divide. Who knew dividing by one could tell us so much? Or at least it's useful to me. Okay. So energy times time. Okay. Oh look. It's giving you the unit of action. Okay. Well, what we're actually doing is we want to divide this, so because we want hour. Is what we're doing. Planck energy divided by Planck time. Okay, it's giving you the Planck power. Duh. Here's the thing. If you scale these things, change it to two. It's going to be the same relationship. You do like 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Boom. Scale it by what was that like 100,000? It's going to give you the same thing. So it's when you go back and you do like Planck flux is 1 over Planck time, Planck length squared. So this is literally the speculative part of the whole like project that I did for the Wolfram Summer School. All right, dimension of flux. So wait a second, you're talking about energy and momentum flux through the causal graph. I'm like, when you do the calculation, all they're taking is this big. They actually take a number that's like I think 10 to the 113 or 10 to the 116, and they take the square root of that. I'm like, wait a second. What if the actual flux of the multi-way system? What if it was the Planck flux? So then I either need to divide by those units or literally take it literally. Take this whole dang factor here. I know it's 10 to the 112. Take the square root. Gives you this number here. I like really didn't even do a thing. I just, I literally was given, you should think about it this way energy. Divide out energy. Oh, it gives me that calculation I had right there. Stephen Wolfram's like assigned homework. You should read these things. Okay, I read those things. Well, it seems to be what's describing. Looking back at the calculation, it's like, what if I took it literally? Plug that in there. You plug that in there. Those are those little units that we're relating right there. They're scaled by the same factor, so it's dimensionally coherently just going to return the same thing. Okay. One blank power. That's a lot of watts. So how much energy is that putting out? So this is expressed in watts, which is energy per second. So all we do is we multiply it by seconds. So it's going to give us the energy output per second. Okay, so it's going to be putting out 3 times 10 to the 50 joule. I have no idea what that is. Comparison is energy. Putting out 2.5 at 2 times 10 to the 5. So basically 100,000, 200,000 solar masses per second. So, aka it's putting out this much mass per second. So, coincidentally, let's say if we took something, we're just going to steal that term. Say Sagittarius. Sagittarius A star. What the heck is that? That's what we believe to be the super dense compact object at the center of our galaxy. Okay. So let's just take the take its mass. All right. 8.5 times 10 to the 36 kilograms. For those of us keeping track of the exponents, I think you all see where this is going. You divide it by that mass term, that's 10 to the 35, i.e., according to the Wolfram Physics project, if you're outputting the Planck power would output the mass energy of Sagittarius A star in about 21 seconds. Yeah. What does that mean? Great question. I could speculate, but we've been going for over an hour. I'm supposed to be talking more about time. God. Oh, excuse me. Length. God, length, time. Why is it so confusing? Why do we seem to be able to trade off? These are good questions. Hopefully somebody can figure this out while we're around. We could find some satisfactory answers. Yes. Because saying, what is it? Planck energy times the Planck length. Ah, let's go back. Boom. We get our. We just. We don't. That's the thing. You look at different formulations. It's like, all right, where's this leading? It's Planck energy times. Oh, sorry, Planck length. Planck length. It gives us h bar c, the elementary unit of action times the speed of light. So, okay, we're gonna do one more little thing, just because Rick brought it up. So, I have no idea what to make of this. So I'm gonna ask you all for some help. Actually, I admit I think I'll send that stuff tomorrow. So okay, so it's equal to h bar c, 1 h bar c. See, look, we've got a 1. Hey, one better. H bar c. I'll throw in a little protective brackets. So thing is, I may be a wee bit obsessive about different things. All right, let's do this. So we've got this. All right. So being the type of person that occasionally with an RPG may or may not check almost like every bookcase and stuff until it becomes perhaps untenable, but I have a habit of trying to check everywhere. I click more. So I see this thing here. It's like, all right, you get this thing, kilograms times meters cubed, divide by second. What the heck is this? This is essentially bending stiffness. Well, it seems that the bending stiffness is stuff, aka our dimensions are mass, length, so basically a volume term divided by time squared. Rick has pointed out this is basically just gravity with mass in the numerator. Why? Well, if you just took this and you divide by the like mass squared, we're going to cancel out the mass that's in there, and we're going to put a unit of mass in the denominator. Bada boom, bada bang. We got the Newtonian gravitational coupling constant. Okay, but that's not where we're going right now. That's an interesting thing. I'd say it warrants further exploration. You got this thing. It's there. 197.3 electron volt nanometers. I have no idea what that means. It's okay, whatever. It's essentially Greek to me. Okay, yeah, it's some units and stuff like that. It's equal to one. That is first. That what is the one? A good question. I keep that in mind. And then it's 1 over 2 pi, the Planck constant, because we're doing h bar, so h bar c, blah, blah, blah. Okay. Get this interesting thing over here. I'm looking at this, I'm like, this number looks familiar. It's like, you see, okay, you see this 3.16, okay, essentially units, okay, it's joule meters and stuff. What the heck is this? Image potential energy constants. Okay. So you click on this. And, oh, where is it? Maybe it was here. So here's the question. You look at this, you're like, what is this? So I'm looking through, I'm like, I don't know. So how did I go about this? Hold on. I need to open up something else. I have some tabs. I'm trying to think about the best way to explain this. What did we do? Okay, I won't belabor the point. Let's just get right to it. Okay. The long story short, I saw this and I'm like, where have I seen this before? And then I'm like, kind of reminds me of when I did some other naive calculation. When I used a particular term that I couldn't really justify and wasn't really sure, other than, well, this seems to be the case. You put in 1/4 of the line structure constant, you get, oh, look, one image potential constant. Wait a second, wasn't that a factor I needed to put in to, like, quote unquote, hack the at least the root mean square radius, at least to how it's been measured within the uh, error bars of the classical proton radius. Because you're really just quantifying the proton's mass and electric charge, and then when you multiply by 1/4 the fine structure constant, you coincidentally do get out what we've technically measured the radius of the proton, or at least the root mean square radius, whatever the heck that is, to within the error bars. It's like, all right, haven't we had about 10 significant digits of the proton's mass for a while? And if we've known it's been about 4 of those charged, or is that something new, like 4 of its Compton radius? Okay, so we have 1 here. Now, again, this is interesting. Maybe there's some there. I don't know. So what blows my mind is this. For those of you that have done a very large amount of calculations or gone down a number of Wolfram holes, you you may be recognizing this as something familiar. So it might not be in. Let's just do this. So coincidentally, if I'm going to do the reckless thing. We're just going to strip off those things. We're going to do a very naive thing. We're going to put the decimal point there, and where the heck is my 137? Because it it looks coincidentally. Uh, I mean, this is at least pretty close to at least what they're modernly measuring the fine structure constant by. If that's calculation puts you at a 7. If you divide by root 2, you do get the 6, and then a little bit closer to measurements there because oh, hold on, where are I at code data? So all right. I'm just saying we can even just do the inverse fine structure constant. So, okay, again, we got a little bit of error there and where? Hold on. Let me look at the other way. I feel like that looks different. Oh no no no. Okay. Oh, the error bars are a little. Okay, no, that's what it was. Sorry. Okay, all right. 137.035999177. All right. So at least here we have 137.0359991. Okay. And again, once we get past like the ninth significant digit, that's where people start to argue. Again, what it is. Again, the only reason I notice is just from remembering it's like, all right, 137, and then it's like 0.35, and then there's three nines, and then it's one. I think that calculates zero. The old one was like a two or something. It's again, only reason I remember was that 35999 thing. It's like, okay, why the heck is that there? Again, maybe this is just a numerical coincidence. I look for this dimension, like you literally, if you look for this, I'm like, all right, this is obviously something that people have to know. You go into the Googles, it's just like, all right, throw that in there. Huh. Okay. Uh, I want to see it with this number. Doesn't seem to exist. So it's like, all right, take off a significant digit. Okay. Take off another significant digit. Okay. Take off another significant. Okay. We have some stuff. Cathode body. Okay. Ah. Oh, is that actually just the answer? Because they're showing. Oh no, this is just. Wait a second. Oh yeah, no, that's the equation. That's Hold on. I think this is where the Google AI was actually useful. So here's what it did. Listen, people will hate on a lot of LLM assistants. I'm like, listen, if it's a noob like me and I don't know what's a thing, I find it useful. Maybe you don't. Hey, power to you. So interestingly, where is it? Nanometers. Okay. I'm pretty sure it told me something different before. It told me it was part of that equation that it's showing right there. That's the hold on. Uh the it's something I've never heard of. I think it has to do with the Wilmore energy. No, no, the Wilmore energy was a surface energy. Sorry. It's where are we? Mm, Is it this guy? No. It was this guy. So basically that's the equation. It's elementary charge divided by 16 pi. So basically you're talking like a surface area there. Uh, or at least there's a 16 pi factor for like a Schwarzschild black hole when you're trying to go to its surface area, and then just times the electric constant, and then it gives you these numbers. Now, from what I at least saw, is there don't seem to be a lot of data on this because uh, okay, the Fowler Nordstrom equation. Here's where we go. Okay, So I had to look that up, and again, it's like it's so, so basically it links to field electron emission. I'm like, wait. Why is this here? Apparently, as you can see, it's there once, twice. It's in field electron emission article on Wikipedia at least twice. Apparently, it's supposed to help figure out what your probability of electron tunneling through stuff and things. Okay, so AKA, where is it? You see over here, what is the S then? The Norheim barrier. Okay. The elementary charge over 16 pi epsilon naught, and then your X is, I think, your valuable there. It's oh, in the X direction. Okay, so it's something. Like there's all I know is I need to learn, but I just come across things and I'm like, ooh, things I can play with. Such a noob. Okay, so basically, I'm like, okay, what does Wolfram Alpha think of this? Because well, it's a computational knowledge engine. Been told it's a superpower somehow because I don't know. Is it? Uh, the Fowler equation? Huh. Oh, B image energy? It was whatever, what is it? Image potential energy constant. There we go. There we go. So basically, it's that equation, or at least this is how it gets characterized in here. So the thing is, what you get here, now I don't know. I don't know. Again, I don't have an exhaustive research on this. No. What seemed to be happening is, again, there seem to be like 7 results, at least according to Google. So you continue to delete. You go down further. Okay, you're seeing the structural and electrical characterization. There's like actual technical papers on things and what seemed to be happening, like when I did another significant digit. Long story short is, I think if I put in 3.6 there, because if you're doing engineering things on that magnitude anyway, I think 3.6 is probably going to get you most of the tolerances you want. Um, yeah, 3.59, 3.9. I think, yeah, I think if I do 3.6, might give us a few more things. Okay, give us a lot more things. Okay, never mind. You still have it. Because I think there it just gets consistent value of A. Okay, the evolution of epsilon, alpha, and band gap as a function of number of iterations. Uh, okay. Is alpha a variable? Is that the fine structure constant? Uh, Optimum alpha 1 over epsilon infinity? I, all I know is that seems to be the tail end of the fine structure constant without 137 there. I think, what is it? In those units, I think if you go to 10 to the negative 7, it ends up electron volt nanometers because that's 10 to the minus 9. Uh, Nanometers is 10 to the minus 9. That's 100 nanometers. So it's, boom. It just so happens to be 10 to the minus 7 meters. Okay. At 10 to the minus 7 meters, we get, is that the right magnitude? No, 10 to the minus 29 joule meters. Oh, no. We go down. Don't mind me. I'm just talking hot garbage there. Okay. I did something. Sorry, I'm getting tired. Probably means I should end the stream. But I just thought that was interesting. I'm like, wait a second. Sometimes like you'll see like what's it like the inductance of quanta. Spelled that wrong. Okay, so two elementary charges divided by Planck's constant. So yeah, you could rewrite that as like h bar and this that there. Because h bar, then you would actually have to have oh, it would be 4 pi. Electric. Oh, that actually might make more sense. All right. Uh, but long story short is you'll see things like the giving us more. Because sometimes you'll see the fine structure constant or like that double seven. It will be the equivalence of something here, something there. Oh, inductance of quantum. Do not. You give me more relationships, or is that it? Okay, so they're not giving the like 20 or something relationships they had before. Uh, but you'll see it, or you'll see like a factor of like 4. You'll see some that's about 137 difference. So it's like you'll see it like that. I've never just seen like that many digits, and it's like again maybe just a complete coincidence. Why is one be image potential? Like I don't know. Where's my 137? I don't know. I just say the only reason I knew that or just thought to do that was just because it's like that was the same thing you run up with that little proton calculations. You just had to 1/4 of alpha to get to be a thing. Now, I think that's cool. Is that an explanation for why you do that with like a proton and a neutron to get, or at least attempt to conjecture what the radius might be? Maybe. I just I have no idea why that's there. Again, maybe that's just nothing, but I think it's pretty cool that where are we? Uh, we just H bar C is the equivalent of that. So all right, H bar C, but that's just gravity basically with a Planck mass in the numerator divided by 1/4 of the fine structure constant, and you get one of these, which is this, which leads to this. I enjoy numerology. Now, is this telling us something? Are these just mild coinkydinks? I mean, why would it have that many die? I don't know. I don't. I'm just a pattern recognition creature. I just remember certain amounts of some interesting areas of digits sometimes, and magnitudes, and then I'm like, all right, well, to be fair, when you express in these units, it's also a magnitude of 1. But actually, no. To be fair, no, that's electron volts now. Okay, well, actually, no. When you express in those units, it's just showing a 1, but it's normally 10 to the minus 29 these units and stuff. So it's like, what does that actually mean? Could we learn something from the, oh God, what do we call it again? The image potential energy constant, which apparently is 1/4 of alpha times h bar c. Because if, actually, it's h bar c. H bar c, bring back my alpha to me, bring back. And again, probably nothing, but I just thought it was interesting. That's like, wait a second, I can look at this stuff, and the only reason I had any idea is just Wolfram Alpha told me. It's like I see this, that doesn't mean a dang thing to me. That doesn't mean a dang thing to me. I can kind of see that just because I played around before, but again, that doesn't mean a thing. That doesn't mean a thing. I had to look that up on Google and then do a calculation. It's like, that's bending stiffness. I don't know. Is this some type of interesting interaction between alpha and gravity or something? I don't know. It's H bar and C, but it's not a today solution. It's not a today solution. Oh, thank you, Rick. I don't know. I'd meant to send this to you with that just because it's like I'm looking. It's a lot of times. It's like I just make errors. I look at things. And I'm like, oh, I look at this, and a lot of times like, oh, two significant or three significant digits. Like, oh, 6.28. It's got to be 2 pi. And then you're running on, and you have like sharp deviation. So it's like, all right, am I going to reject something we have like 7 to 10 digits of precision on because it matches by like two or three significant digits of 2 pi? Or am I going to assume that maybe there's more to it? Now, truth be told, very often I'll get discouraged at things and I don't know, and then I'll talk to somebody and then have conversations, and eventually I'll look at something in a completely different mindset and just kind of like go through and be like, oh, well, this is far prettier and easier to interpret. Do I know what this interpretation is? Oh, I just thought it was kind of cool, and somebody can figure out what might be going on there. Hey, please let me know. I'd love to figure it out. But all right, so we're going for more than an hour. Sorry about the Planck Length. We jumped into some different areas and topics, and again, it's like all I know is I just remember Stephen Wolfram at one point. It's like, oh, Wolfram is kind of like a superpower. Why? Because you're attempting to do computational X. That's one of the big things that they're trying to promote now. Uh, in my opinion, from what I've seen, just again, take it for what it's worth, is the computational paradigm, at least computation X, is you can have as much information as possible about a thing and look at it in different ways. It's also the only reason I'm able to do any of this stuff, just because if it has this in a database, it's like I can go through Google and Codan and do all these different relationships, but it's like I actually have to go through and do every single calculation, ask all these questions and everything, and not know what it really is. And the benefit of Wolfram Alpha is at least as a first level approximation. Again, if you want precise calculation, yeah, you go to CodeEdit, you grab all the digits of H bar, you grab all the digits of big G, C, this, that, the other thing, because to note, like it is doing calculations, and it's only going to have a level of accuracy up to whatever data you put in there, and then it will just round and just make up just some random numbers there. But at least Wolfram Alpha is set up sort of like Maple, which, as far as I understand it, was set up for mathematics. So it's I would think that since there are some professional mathematicians there, they would want to use a tool that actually helps them. Perhaps it doesn't have a mathematician's rigor, but at least within the realm of physics, it seems to work pretty dang well. Okay, where are we? Okay, that's basically all I got. So, talking about Planck length seems to be a minimum thing. Uh, again, I happen to have the square root. Rick was talking about radicals. We did a little thing on the channel here about looking at ways to just like radical H bars, radical G's, radical C's, and stuff like that, and seeing how you can combine them. And it's pretty interesting. You might say, "Oh, that's a crazy thing," but it's like, really? It's like these Planckians are literally described by radicals, so it's like maybe it's not such a radical idea. But we will continue with this tomorrow. I think we're going to do charge. Charge. That's where we're at tomorrow. So, other than that, peace out, everybody. Take care of yourselves. Well, wacky and wild world out there, but it's looking to a better tomorrow. Peace out.